Hello students, today we are going to learn about types of functions. Some types of functions you learn in class 11. For example, that is algebraic function, trigonometric function, then that is exponential function, logarithmic function, modulus function, greatest integer function, then fractional function. Here we are going to learn some special types of functions which are in our syllabus. So I start from that is types of functions. In types we have to deal with that is one function. What? One function, or it is also called that is injective function. Or we can say only injection. So what type of functions are called one function? We start a function f from set A to set B is said to be one function if different elements of A have different images in B. It means it is not allowed two different elements of set A have the same image in set B. Or f the function from set is 1 then if we take two different elements, it means x1 is not equal to x2, then it must imply the images of x1 and x2 are also different. It is for all x1, x2 to be the element of its domain. That is called A. And in case when we get two elements such that their images are equal, then by definition of the function it is possible only when the elements are also equal for all x1 and x2 to be the elements of A. This is about the one function. We use as an algorithm to show a function 1 we start from taking two elements whose images are equal, and when we are able to show they are also equal, then we say it is 1. If starting from their images equal but they are different, then we say it is not 1. At the same time, we have one more type of that is function, that is many one function. If a function f is not 1, then it is called many one function. It means at the place of saying the given function is not 1, we may say the function is many one. For example, if I take two sets, that is one is at A, other is as B, let there be correspondence or a function that is f. Its elements are A, B, C, D. Take it 2, 4, 5, 7, 8. If the image of A is 5, B is 2, C is 4 and D is 7, this is actually it is a function f. Then we say it is 1. Why? Since here different elements of A have different images in B. That's why it is called 1, 1. At the same time, if I take example of the function, that is, it is A, B, C and D. It is 1, 2, 9, 7, 6. It is set A, it is set B if the image of A is 9, image of B is 1, image of C is also 9 and image of D is 7. Then it is called not 1, 1. Or we can say it is many 1. Why we say it is many 1? Since images of A and C, that is 9. That's why it do not follow the definition of that function. So let's take some more example of 1, 1. If I take, let f be a function from set of real numbers to set of real numbers defined by fx is equal to x cube. Then just what's one way to check it? This is rule in maths. If we want to prove it, then we prove in general, and if we show it is not 1, 1, in that case we are supposed to contradict. Since it is 1, 1 function, that's why I use the algorithm fx1 is equal to fx2, where x1, x2 are the elements of R, that is domain. Then it implies by definition of function, if here x, then it is x cube. If here we put x1, then we get here x1 cube. Similarly, when we put here x2, then we get x2 cube. So it is x2 cube, and definitely it implies x1 equal to x2. Therefore, f is 1, 1. At the same time, if we take different examples, that is, let f is a function from set of integers to set of integers defined by let image of all those x is equal to x square plus 5. So there is a scope of contradiction. That's why we are supposed to contradict it. It means we have to search two elements of its domain whose image is same. If we take that is minus 2, so definitely it is minus 2 whole square plus 5 and we get 9. At the same time, if we calculate that is 2, it also comes 2 square plus 5, it is equal to 9. From here we get f of minus 2 is equal to image of 2 under f, but minus 2 is not equal to 2. Therefore, f is not 1, 1. It is many 1 function. Since this is the situation, here if we are having this side, this is this side, here we are having minus 2, 2 and here we are having 9. So this is the image of minus 2, it is also the image of minus 2 under f. That's why this type of function is many 1. Since when we take simple example, that is modulus function. Modulus function means it is defined as fx equal to that is, and actually it is a function from set of real number to. Again there is a scope of contradiction. If I write this is minus 1, then it is equal to, and it is equal to 1. At the same time, it is 1 equal to 1 equal to 1. It implies f of minus 1 equal to 1, but minus 1 is not equal to 1. Therefore, modulus function is not 1 1. Next example, if I take that is greatest integer function, that is greatest integer function, it means that is fx equal to, that is by definition it is the greatest integer less than or equal to x. So here if I get the value of that is 1.3, then definitely we get 1.3 and it is equal to 1. If I write that is 1.4, then it is by definition of function it comes as 1. It means this is the situation. Here we have 1.3, 1.4, image 1, it's also image 1. This is the function. Since f of 1.3 is equal to 1.4, but 1.3 is not equal to 1.4. So it is many one function. Now some formulas are there. If f from A to B is a 1 1 function, so there are some restrictions. If it is 1 1 function, then in that case, since different elements of A has its different images in B, so that's why number of elements in set A must be less than or equal to number of elements in set B. In case when n number of elements in A equal to P, number of elements in P equal to Q, then number of 1 1 functions from A to B, it is equal to, in case when this condition is not satisfied, then we are going to what? Not a single 1 1 function. It means when that is P is greater than Q, the number is 0, and if P is less than or equal to Q, so its number is Q by Q minus P factorial. If number of elements in A equal to P, f is a function from A to A, then number of 1 1 functions is equal to, it is very simple, P factorial. This is about the number. Now just take other example. Next one is that is on2 function. What? On2 function. It is also called surjection or surjective function or surjective function. This is a set A and this is a set B. Only simple condition is there. Set B is entirely used up. This is simple condition. It means there is no element in set B which do not have its pre-image in set A. So a function f from A to B is said to be onto function if every element of B has a pre-image in A. Mathematically we can say it is very easily, that is it happens when fa is equal to what? That is set B. Or we write more clearly, that is range of function equal to codomain of f. It means if here I write 1, 2, 3, 4, that is 6, 2, then 8, and it is 4. So image of 1 is this, 2 is 4, 3 is 6, and that is. So we see here it is a function. No element in B is what? Not having pre-image in A, or we can say its range is equal to the set B. That's why it is into function. At the same time we have what? Into function. Into function. If a function f from set A to set B is not onto, then it is called into function. For example, if I write here, that is set A, it is set B, that is A, B, C, D, then 1, 6, 9, 5, 7. 1, 6, B image 1, C as it is into. Why? Since 6 and 7 do not have pre-image. This is about into. Okay, this is about unto, this is about into. It means, so what is the criteria to show the function given is always unto? In case of f is a function from A to B, f is a function from A to B. So in that case, number of elements is always greater than or equal to number of elements in B. Okay? Okay, if NA is equal to P and B equal to Q, then number of onto functions is equal to. It is divided into two cases. When P is what? That is less than or equal to. If it is greater, then that's okay, it happened. If it is less, then that is impossible. So just divide it. If P is greater than or equal to Q, then it is sigma r equal to 1 to Q minus 1 power Q minus r QCR, and that is r power T. And if P is less than Q, then 0. So if f is a function from A to B, A to A, such that NA equal to P, then number of what? Onto functions equal to P factorial. So we use this formula if domain and codomain are same, and if they are different, then we use this one. Okay.